to switch to another paper, and let me introduce the presenters. Professor Michel Grabish from Paris 1, University of Paris 1, Sorbonne, who is a very good friend of mine, and it is my great pleasure to introduce him. Professor Grabish is one of the leading scientists in decision analysis, always published top-level papers in different journals, you see, and another thing which I cannot skip, he also plays very good piano. So that is really, it's a great pleasure. And when he was our guest in Moscow, he played in our concert hall, and I have his records, and I hope in the nearest future he will come and give us another concert. Michel, floor is yours.
Thank you very much, Fuad, for your kind introduction. Thank you for the invitation. And good morning, good day to everybody. So maybe I should share my screen now for the slides. Yeah, here it is. So can you see my screen?
Yes.
Okay, so I will start now. So it works, yeah. So this is, let us say, a survey of methods in multi-criteria decision making, dealing with interactive criteria. So the talk will be divided in 3 parts. In the first part, I will explain about multi-attribute utility theory. Then I will introduce shock integral, which is the main tool here. And then I will try to formalize the idea of interaction between criteria. So we start with very standard and classic things. So I consider a number of attributes. X1, X2 to Xn are the set of values taken by the attributes. And capital N will indicate simply the index set of these attributes. So now if I consider an alternative, it's just an element of the Cartesian product of all these attributes. And so an alternative X is simply a vector in this cross space, in this Cartesian product, okay? So just to illustrate, you can think, you can think these are, for example, computers or cars or whatever, and the attributes are just descriptive attributes for each element. For example, if it is a computer, then it will be the speed of the processor, the price, size of the memory, and all these things, okay? So it can be very diverse. So now for the notation, if I consider a subset of attributes A, then I can, by using this notation, divide the vector X into 2 components, into 2 parts, let us say. So X sub A is just all the coordinates which pertain to the subset A. And when I indicate minus A, it simply means that I consider the attributes which are not in A, okay? So taking here 2 alternatives, X and Y, I can split in 2 parts, taking X for the part pertaining to attributes in A and the alternative Y for the attributes pertaining to all other attributes those not in A. Okay. So now I consider that we have a decision maker, and this decision maker has a preference relation on X That is to say, the set of all possible alternatives. And this preference relation is assumed to be complete and transitive. So the aim of decision theory, we can say the following: given a preference relation, then I want to find a numerical representation of the preference. This by the means of a utility function. And so we simply say that U, the utility function, represents the preference if the following condition is satisfied. Each time I prefer X to Y, then the utility of X is at least as large as the utility of Y, and conversely. Okay, so we will come back to this later. We call this ordinal measurement because we measure something, so we transform abstract objects into numbers. This is measurement. And ordinal because we just take into account an order. So we order the objects and then we give a number to them. Okay, so the one of the most simple model is the additive utility model. We simply decompose the utility function on the Cartesian product X into a sum of marginal utility function UI on every attribute. So this is the simplest, one of the simplest possible model. So now let us introduce some properties for the preference relation. So let us take a subset of attributes A, and we say that this set is preferentially independent of its complement if the following is satisfied. Or let us look what is written here. So you'll see that for attributes in A, you have two different alternatives, X and Y. And then for the rest, you have something called Z. Okay, so suppose you prefer this compound alternative to this one, then the property says that, in fact, it changes nothing if you replace Z by some Z prime, whatever Z prime is, okay? So in some sense, the preference over the attributes in A is independent of the preference for the other attributes. This is the meaning. Now, suppose that this property is true for every possible subset A, then you say that the attributes are mutually preferentially independent, which is, of course, a very strong property, which you cannot guarantee in any situation. So, for example, let us take this very simple example of evaluation of students. So suppose you have to evaluate students with respect to three topics, which are mathematics, physics, and language skills. Okay. Suppose you have 4 students, A, B, C, D. Let us look for student A. Let us examine students A and B. So you see that grades in mathematics is relatively low. Grades in physics is large for student A, and average for language skills. Okay, and it is the opposite, exactly the opposite for student B. So suppose that in this diploma you favor more scientific topics, then you will say that student A is better ranked than student B. So you have this preference. Now you look at C and D. Observe that for physics and language skills, it's exactly the same marks on A and B. But now the score in mathematics is quite good, okay? And so maybe you will change your mind. Now you will say, oh, but then I prefer student D because this is a more balanced profile, between sciences and language. And so you may say that student D is finally better than student C. This example cannot be modeled via an additive utility model. Okay, so we will take this example later and solve it with our tools. Okay. So, given these examples, we may say that when attributes are not mutually preferentially independent, then there is some interaction between the attributes. And if there is no interaction, then there will be mutual preferential independence. Okay, so this is the first attempt of definition, which is summarized here. Okay, so let's continue. Now, since this property of mutual preferential independence is very strong, we weaken it into the following. We speak of weak preferential independence. It simply means the following. It simply means that any single attribute is preferentially independent from the rest, from all the other attributes. So in formula, it's following. So if this says the following, suppose you prefer this alternative to this one, and you see that the only difference between the two is that on attribute I, you have a value X, and here you have a value Y, and you prefer this one to this one. Now, weak independence means that you can replace Z, so the value of all remaining attributes, by any other value. It does not change your preference. So this is weak preferential independence. So why is this property very interesting? Because if this is true, then you can define a preference relation on the attribute number I, because now it's meaningful to say that xi is preferred to yi, because you take any element z, and if this preference is true, then it will be true for any z prime. Okay? So this defines in a meaningful way a preference relation on a single attribute. Okay, then if you are able to do this under some measurement condition, under, for example, order density, you can build a marginal utility function ui on this attribute. So since this holds for every attribute, then you are able to build all marginal utility function u1 to un. And the decomposable model is the following. You say that in this case, the global overall utility function u is just a combination of the marginal utility function. The combination is done via some function f, which we will call an aggregation function. Of course, this function has to be increasing and even strictly increasing. So this is a decomposable model, and all the rest of the talk will suppose this model. So it means that we suppose this property. Otherwise, we cannot build what I will explain. Okay, so this is mandatory. Of course, we know there are some famous examples where this property of weak independence is not true. So this is one of the very classical example. The menu example, when you have to choose between red wine and white wine, and you choose your dish, and everything is dependent on the other choice. So in this situation, you cannot guarantee that weak independence is satisfied. Then you have to do something else. But okay, we don't consider this. So now let's go to the second part, where I will present the main tool, which is Choquet integral and multilinear extension model. So one of the most simple decomposable model you can imagine is the weighted arithmetic mean. So the function f is simply this so well-known weighted arithmetic mean. In this case, so you just put weights, positive weights, summing up to 1 on each attribute. So you can consider that these arguments of the function are the scores of some alternative on the different criteria, and you just aggregate these numbers, because these are numbers, yeah, by this arithmetic mean, simply. Okay. So this is exactly the same as the additive utility model I've shown in one of the first slides. And since the additive utility model implies mutual preference independence, you see that the additive model cannot represent interaction by definition, by our definition of interaction, by the fact. Okay, so what we propose is to generalize this by what is called the Choquet integral and the multilinear extension. We will explain this in a moment. So let us take a very simple example. We take 3 alternatives evaluated on 2 criteria, on 2 attributes, okay, only this. So A, B, C, here are the scores obtained on each attribute. So alternative A obtained a score of 0.4. Let us say it is in the scale 0, 1. So 0.4 is a little bit below the average 0.5. So it's not very good score, but not very bad either. And for alternative B, the situation is extreme because on the first attribute, the score is 0. So it's totally unacceptable. While on the second attribute, the score is equal to 1. So which is the highest score you can obtain. Okay, and for alternative C, it is exactly the opposite. This alternative is excellent on the first attribute and very bad on the second one. So, given this situation, the choice is not obvious to do, but suppose that to the value 0, you consider that the value 0 is not acceptable, then you are more or less forced to take alternative A as the only reasonable one. It's not excellent, but at least is acceptable in some sense, which leads you to the following order. So A is strictly preferred to B, which is indifferent with C, because it's difficult to rank these two. So now, suppose you want to model this preference by a weighted arithmetic mean. It's very easy to see that this is not possible. Whatever the weights you will put on the 2 criteria, it's absolutely impossible to put alternative A ranked the first, because what you will obtain is overall value of 0.4. And here you will you will not be able to rank them after. Okay, so the solution we see to this problem is that maybe it makes sense to put not only weights on the single attributes, but also to put a weight on both attributes together. Okay, so it will be a weight on the group of criteria or attributes 1 and 2. Because if you put a weight on this group, that it means that for you it's important that both criteria are satisfied. Okay, and if you put a very small value, it means that you are not so much interested into having both criteria satisfied. Maybe only one of them is enough. So you see that you get some flexibility on your preference modeling. And in fact, what you will do is exactly this, but in a very general way. So let's introduce now formally the things. So again, I remind you that capital N is represents the set of attributes, just the index set. And now you define a capacity on N. So what is a capacity? Was something introduced by Gustav Schoke in the 50s, also rediscovered by Michio Sugeno in the 70s under a different name. And so what is it, mathematically speaking? It's just a set function. So to each subset of N, which means a group of attributes, you assign a numerical value, which is more or less the weight you put on this subset. So you just impose two properties. The first one is a normalization. So you put value 0 for the empty set. You put 0 for the empty set because if there is no attributes, of course, there is nothing there is no importance. And for all attributes, you put the total value 1. And the second property, which is very important, says that if you take two groups of attributes S and T, if S is included in T, then V of S should be smaller than V of T. So if you interpret V as a kind of importance of the subset, this property is very natural because it says that if you add some attributes to a subset, of course, the importance cannot decrease. Yeah? So in monotonicity. So a very simple case is additivity. If you take two disjoint subset of attributes, then its importance is just the sum of the importance of A and B separately. So this is additivity. But of course, as we will see, additivity is very restrictive and it will amount to the simple additive model. So we will not consider it. So now about can we be more precise on the interpretation of V? So roughly speaking, okay, V represents the importance, the weight of importance of a group of criteria. But this is only intuitive. So now we should be able to give a very precise definition, which is here. So now suppose that you fix some particular elements on your attributes, which we denote by this bold 1 and bold 0. So these are not necessarily numerical values because depending on the attributes, it can be something qualitative, not numerical. Okay. But the meaning is important. The meaning attached to these two levels in the attributes is that bold 1 represents a satisfactory level. So something you are completely satisfied with it. And 0 represents unsatisfactory level. You are not ready to accept, okay? And then you just normalize your marginal utility function based on these elements. So you say the value, the utility of the satisfactory level is equal to 1, and the utility of the unsatisfactory level is 0. Okay. Then you define V of A. So in some sense, the importance of set of attributes A as the overall utility of this special alternative, which is formed of two parts. On attributes in set A, you put the satisfactory value, and on the remaining attributes, you put the unsatisfactory value. So it is a virtual kind of virtual alternative, which not necessarily exists, but you imagine to have it, and you put an overall score, an overall utility value on it. And this numerical value is defined as the value of the capacity on the subset A. And since, and we also impose the following, is that since we take a decomposable model, so you remember the decomposable model, the overall utility function U is equal to function F aggregating all marginal utilities. And thanks to this normalization here of the marginal utilities, then this vector of attributes is transformed into this vector of numerical values. Okay. So now if we look at the things more mathematically, we say that it says the following. So V, the function V, which is a set function, and the function F, which is an aggregation function, they coincide for these vectors. What are these vectors? Simply vertices of the hypercube of the dimension n. So in other terms, supposing that V is known function and F is unknown function, then F can be considered as an extension of V on the whole hypercube. Okay, so again, supposing V is known, okay, then F can be considered as an extension. Okay? So for this reason, it makes sense now to look at extensions. Yeah, so to do this, we need some additional notation, but it's just very simple. We identify subset S of a given set N with a characteristic function. So simply the vector, 0, 1 vector, where you put value 1 for all elements in S and value 0 otherwise. Then you can identify capacity V with what is called a pseudo-Boolean function. It's exactly the same object, but written differently. Okay, so again, instead of considering V, a set function, so V of S, you consider now a numerical function F, taking as input only 0, 1 vectors. Okay, and so we have the following. So suppose you have this pseudo-Boolean function, so defined only on the vertices of the hypercube, and you can get easily. So first we can rewrite it. Let us rewrite it first in this quite complex form. But if you look, it's in fact it's very simple. So let us take a vector on which is a vertex of the hypercube simply, and now so suppose that X Yeah. Okay. So now the mic is working again. So what you see here is that if X is corresponding to the set A, then in this sum will remain only the term of f of 1a, because this term will be equal to 1 and this term will be equal to 1 only in this case. So now this can be considered as a polynomial expression, and you can factorize it in a different way. So if you develop and refactorize, then you can obtain this form, which is also polynomial, but of course the coefficient here will be changed. It will not be the same. And what is interesting is that these coefficients correspond to what is known as the Möbius transform of the set function V. And here is the exact expression of the Möbius transform, that is to say, these coefficients. Okay. So now what I am telling this because I just want to obtain extension of the capacity V. And via these two formulas, no, especially this one, in fact, I can obtain extension, which is explained on the next slide. So the first extension, you see, if we compare with the previous expression, it's exactly the same. So I just replace now X, which was only a vertex on the hypercube, by any point in the hypercube. And the definition absolutely makes sense. And if you do this, what you obtain is called the multilinear extension, also proposed by Owen in game theory. So now you can replace this expression with this one, because the minimum, this is the minimum operator, yeah. Minimum and product coincide on the vertices of the hypercube. So now you can consider this second formula with elements inside the hypercube. And so you have a second extension. It happens that this extension is nothing else than the shock integral. It was also rediscovered by Lovász in combinatorial optimization. And so this is why it's called Lovász extension. So now we have two models at hand, the multilinear extension and the shock integral. Okay, so now we would like to know what is the difference between the two. So because if we do decision making in the usual way, you must not forget that what is given is only the preference, and then you have to derive your model from the preference. Since now we have two different models, we should know when I must use one of them and when I must use the other one. Okay. So, and it's possible to answer to this question by, again, we have to go back to measurement theory, and especially difference measurement. So this complicates a little bit the things. So maybe I will not insist too much because time is running. For this, I need not binary relation, but quaternary relation, comparing pairs of objects. Okay, so X and Y are alternatives, S and T are other alternatives, and you compare this pair of alternatives with this one. Okay, and the meaning is that it's simply the difference of intensity of preference. So in words, the difference of intensity of preference between X and Y is greater than the difference of intensity of preference between S and T. So this is the way you should read it. And difference measurement consists in finding a numerical representation in this sense. So supposing xy is greater than st in the previous sense, then you see that with utility function, the difference here should be greater than the difference here, okay, which exactly translate what we have said here. Okay, so now, yes, ordinal measurement was similar but much simpler. And yeah, so let us turn to this property. So you remember the property of weak independence. Now we introduce similar property, but extended to pairs of alternatives. So the notation is a little bit terrible, but the meaning is really the same as before. You just take 4 alternatives x, y, z, w on a single attribute, you consider them. And for the remaining attributes, you consider some vector t, whatever it is. And if this preference is true, then by changing t to t prime, this does not change the preference. And so exactly as before with weak preferential independence. And under this condition, it can be shown that the unique models representing your preference is the multilinear extension model. So in summary, if I take again ask again this question, the answer is the following. If you satisfy weak difference independence, you must take the multilinear extension model. If not, in order to use the shock integral model, it's not free. You must have attributes which are commensurate. And this is it's a little bit difficult to obtain. You must absolutely define absolute levels on each attribute, as we did already before with the bold 1 and bold 0, if you remember. These were interpreted as satisfactory and unsatisfactory levels. So you must absolutely define this in order to use the shock integral. So now we go to the last part. So the modeling of interaction. So we will use several ways to address this question. So the first one is to go directly via the capacity. So remember, the capacity is expressing all the importance on the subsets of criteria. Okay. Let's see what we can do with this. So let us just take 2 attributes, only 2, I and j. And I say that there is positive interaction between I and j if the following is true. Look at this difference. So remember, V represents the importance of the attributes. So it says that the difference of importance of the attributes n, s plus I and j, so you add 2 new attributes I and j, this difference is greater than the sum of the individual difference. We could interpret as the difference as a kind of marginal contribution of the attributes I and j. So this is the marginal contribution of I. This is the marginal contribution of j. And this is the joint marginal contribution of I and j. And what the inequality says is that the joint marginal contribution is greater than the sum of individual marginal contribution. So in this case, we say there is positive interaction or positive synergy. Now, So this expression can be simplified because one of the VS can be removed. And then you get this, which is a very nice expression. So you have I and J here, I alone, J alone, and nothing here, okay? With alternate sign, plus, minus, minus, and plus. Okay? So now we can imagine the opposite situation where, in fact, you have the reverse inequality. So it means that the sum of individual contribution is greater than the joint contribution. And then we speak of negative interaction or negative synergy. So you have the opposite inequality. And we can also say that in case of equality, so there is no interaction. And we can consider the attributes as independent. Independent in some sense. We don't know exactly what it means, how to relate this with the previous properties I want to say. Okay, so this is fundamental. And you see that this is defined with respect to some subset S. And so the question is, but what happens if I take another subset, S prime or whatever? This is why we need to take a kind of average of this quantity. So remember, this quantity was, in fact, the comparison of the joint contribution and individual contribution. And so you take every subset S, not containing I and J, and you weigh this by some combinatorial coefficient here, which looks like to the coefficient used in the Shapley value for those who know the Shapley value. Okay. So this was in fact proposed by two people completely independently. So Guillermo Owen in game theory, in a paper which was left unnoticed for a long time, and by Murofushi and Soneda in a paper written in Japanese, also relatively unnoticed. So now, if you look at this, it's tempting to generalize the definition to any subset of attributes, not only two subset I and J, but I can take three, I, J, K, and more or less. If I take only one attribute, then I get the Shapley value. And otherwise, I must consider more attributes and generalize my formula, which is here. This is a general form for any subset of criteria. So this interaction index contains as particular case this one and also the Shapley value. So let's go back to our example. So you remember the previous example. And now we are able to solve it because let's think about modeling. So if we interpret what was said before to explain the ranking, we could say that mathematics and physics have a negative interaction between, because here we would say we have said that it's kind of redundancy here, while there is positive interaction between physics and language and mathematics and language. And so I can model this simply by these figures. Look, these are the individual importance of mathematics, physics, and literature. This is a combined importance of mathematics and physics. You see that is smaller than the sum of these two numbers, while 0.7 is greater than the sum of these two numbers, which represent positive interaction and here negative. Okay. Then I apply the definition of shock integral and I find the following overall score. And you see that A is ranked before B and D is ranked before C as wished. So we have succeeded in a very easy way to model the preference of the decision maker. So now maybe I will skip some material here because time is running. What is say here? This is mathematical, in fact. It is the notion of transform.
Michel,
Yes.
you have 10 more minutes quietly.
10, yes, 10. Okay, so I have, yeah, I must be careful. Okay. So here the transforms just say that you take any capacity V or any set function, by the way, and you transform it via linear transform. For example, the Möbius transform is such a transform. It means that if you give me V, I can compute the Möbius transform. And if you give me the Möbius transform, I can compute back the original function V. Okay? And in fact, with the interaction index, it is exactly the same. It defines the transform because this is defined for every subset S, including the empty set. And you have a formula to transform it back, which is more complicated, but which is interesting because it involves the Bernoulli numbers. Okay, so I don't detail anymore. So you have other transform like the Banzhaf interaction transform, which generalize the Banzhaf index, and so on. You can also use Fourier transform and so on. I will not detail. Okay. So now what is important here? Let's go back to this interaction and mutual preferential independence. This was the starting point, in fact. So if you analyze the previous formulas, I will not do it, but it's easy to do. Then you will discover the following. If your capacity is additive, then the interaction transform is identically zero except for singletons. Okay. And the same for the Banzhaf transform, in fact, Banzhaf interaction. Okay. And conversely, so you have equivalence between additivity of the capacity and no interaction except for singletons, which is not really interaction. Okay. It's just the Shapley value. And the second fact is the following. Supposing you have 3 attributes at least, then taking the Schoch integral model, mutual preferential independence is equivalent to the additivity of V, something we have intuitively understood, but this is proven by Morofushi and Sugeno. And so now the conclusion, if we combine the two facts, then we have an equivalence between interaction, no interaction, and mutual preferential independence. What we exactly said at the beginning. But now we were able, now we have a mathematical definition of interaction, and this definition match with our expectations. This is important. Okay, so now we can take a different point of view. We say, okay, so I have an aggregation function f, and I would like to directly define the interaction with the function f. I don't know about the capacities and so on. Maybe f does not involve capacities at all, so I take any function f. How to define interaction? This is also possible. You just consider what is called total variation. So suppose your function f is defined on some closed interval ab times itself n times. And so you would like, you are interested into knowing what is the influence of attribute I, coordinate I, for the value of the function. So you compute this difference. You compute the difference between, you put the attribute at the maximal value minus the value of the function at the minimal value for attribute I. And you do this for a given point x, of course. Okay. So now you can imagine, you can generalize this. You take two coordinates I and j, and you compute the total variation of the total variation, and you will find this formula. And you can continue, take any subset of coordinates or attributes, and you define the total variation of f with respect to the subset of attributes at a given point x. You don't forget it's defined at some point x. So now we have to consider every possible point x. So we take the integral over the domain of the total variation, and this is defined as the interaction index for subset k of attributes. So apparently this has nothing to do with the previous story. But what is interesting and even fascinating is that the two definitions coincide because the interaction index we have defined with respect to the capacity is exactly equal to the interaction index for the Choquet integral under this sense. So the two definitions coincide. Choquet integral here and interaction index for capacities. Now, if you take the multilinear extension, so you replace f by multilinear extension, then what you get is the Banzhaf interaction index. And this is extremely interesting because it says the following. You have several possible definitions of interaction indices, but this theorem tells you which one you should take depending on your model. If you take the Choquet integral, then you must take the interaction index as defined before. If you take the multilinear extension, then you must take the Banzhaf interaction transform, which is not the same. Okay, so now there is a last way, a third way to recover all this. It is a statistical approach, but I will go rather quickly. So the Sorbonne indices are quite well known, I suppose, in statistics. So because it's a kind of analysis of variance. So suppose you have a multivariate model, y is a function of random variable z1, zn. And so you decompose your function f as follows. So you have a first term is just the expectation of y. Second term is conditional expectation with respect to one variable. Third term is conditional expectation with respect to two variables, and so on. You continue like that. And then you can do an analysis of variance because the total variance of y is simply the sum of the variances of every term in the previous sum. So if looking at this, it seems to have no relation with our previous stories. But here is what is very surprising is the following. So take as function f, the small f, so the multivariate function, take the O1 extension, okay, the multilinear extension. And they compute all these Sorbonne indices, the variances, okay? And what you find is that you get, in fact, 1/3 to the power s of the Fourier transform, which is almost equal to the Banzhaf interaction index. So, you by just using statistical tools, you recover the Banzhaf interaction index. So you see how all the three ways are very closely linked, and this gives some solid foundation to the theories. Okay, so I was a little maybe too fast for all the details. So if you are interested, then you can find much more into this book I published already 7 years ago. So thank you very much for your attention.
Thank you very much, Michel. That was really very interesting. Please, questions. Michel, I have a question. You see, it is this very field is rather far from my activity, but you see, at the very beginning, when you said about this representation of utilities, there might be the maybe you know I can send you my work on this specific type of semi-orders, which I call simplest semi-orders, when we have only one violation of this very utility function, when I have one element which is indifferent between two equivalence classes. Might it be that this very models might be extended for such a specific cases? You understand? My idea is that you see that we have this utility function like a classic case when we have this equivalency classes and they go, the first one is better than the second one, better than the third one, etc. But there is only one element. I call this type of model a simplest semi-order, which is indifferent between two neighboring classes. This neighboring equivalent classes. They have very interesting utility representation.
Yeah.
In fact, I came to these structures from this utility representation.
Yes.
Maybe somebody, nobody considered such kind of cases in this model.
No.
Some kind of, you see, when we have some kind of spoiling this very relations.
No, I am not aware of this. So
maybe we will discuss it separately.
So if I understand well, it would be a generalization where you have maybe the utility function like a shock integral or whatever, but you have also this threshold of indifference, and which will be added, and so this complexifies the model, and yeah, this could be interesting to consider. Yeah, surely. Yeah.
And if we have a question, maybe I ask another question. If nobody has,
I have a small question.
Yes, sure. Please go ahead.
Hello, Michel. Nice to see you. Thank you for your presentation. My question is the following. So what does those results hold if you want to not just to make preferences over alternatives, but over the group of alternatives? Because, for example, in your example with the students, you have attributes and you want to make preferences on the students itself, but maybe your problem is something like the formation of a team of a student for some kind of project.
I see.
And whether your results hold, if, for example, you need to construct some kind of group where one should have mathematics and language, and maybe another one should have language in this group, and you make your preferences over the sets of alternatives, not just the alternative itself.
Yeah, I see. No, I'm not aware of this either. But so if I understand well, it would consist in maybe you have either you have to define another set of alternatives, which would be groups of students, or you must define a second level of aggregation. So every student has an overall score, and then you have to aggregate the score for a group of students. So this would be two way to address your problem, I think.
Yes, that is. I understand Daniel's question as you see to switch to hyperrelations and define this kind of utilities on hyperrelations. In fact, we touch this kind of things in our book with Eiserman, theory of choice, sorry. Mhm. Yeah,
Okay, I see.
that might be interesting also, extension.
I have an observation, just,
Yeah, sure, Manfred.
if you have a voting system and a parliamentary system, and you don't allow coalition formation, you don't allow it, or it does not exist because they have a two-party system, or you don't allow it, then you have this independence. And then, for instance, local monotonicity works. Tomorrow I will talk my gossip about that. But now that seems, there's this kind of relationship. You have this independence, and then some properties work, which of course do not work, if you have dependence. That's just an observation. It's very, very interesting, actually, to me. Thank you.
Thank you very much for the observation. Thank you.
Thank you very much, Michel. It's great, really, you see so many interesting results and extensions. Thank you very much.